Hi, this is Mr. Yeager. This is the electricity section. This is geared toward AP Physics 1. I know I've already done a video with it, really more geared toward on level. There are a lot of similarities, but I need to specify a few more things for the AP level with it. So we're going to move through this, and here we go. Okay. So start off with, again, this is all stuff covered in electrostatics, where, again, just definitions of electricity. We're looking at electricity now, which is actually the movement or flow of electrons, energy being carried by these electrons. There's lots of different definitions. And again, that's versus static electricity that we talked about during electrostatics, where it's just the accumulation of the charge, okay, where it just holds on to it until it discharges. And again, the idea of the electric field, which is that force that's pushing those, which obviously pushes charges away from each other. But again, main thing here is we're looking at electricity in this unit. We're going to look at how do we measure electricity, and then we're going to look at circuits, and then how do we justify why things happen in circuits in particular. So we got a definition again for static discharge, movement of excess electrons, this is sparks and lightning. We obviously are hoping that doesn't happen for electricity, otherwise that's a huge amount of charge going all at once. We want a nice controlled charge, flow of charge. And then we talked about conductors and insulators, which that'll come up again with one of the properties of electricity in terms of resistance, where conductors have a very low resistance, insulators have a high resistance. And we're going to come to a particular measurement of why they have that type of resistance. So let's look at measuring electricity. We already talked again about charge. So again, some of this stuff is review. Charge creates the electric field in an object. The symbol for it is Q at the top, measured in coulombs. Again, that's all review. We already know that, except we're going to start talking about the flow of this charge. The one thing I do like to just mention with it is I've been saying charge, 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 and charge will create a force. And it creates a force because there are these electrons repelling or attracting. It turns out that 1 coulomb is 6.242 times 10 to the 18th electrons. You will never have to use that in AP in terms of ever converting coulombs to electrons or electrons to coulombs, but it gives you the idea of the insane number of electrons that just 1 coulomb actually is. And so that's why there's so much force developed just from two 1 coulomb charges between each other. A very, very, very high force, in fact. Okay. All right, getting more specifically to what we're going to measure in circuits, the first one is what's called potential difference. Its symbol is V. So when I say symbol at the top here, all right, the V, what I'm referring to is that's the symbol used in the formula. It's not the unit, it ends up being the unit. But when we're going through these, I'm going to show you symbol, what it is, and then the unit for it down below in the wording. So this is called potential difference. You probably know this simply as voltage. If you ever hear about something having 12 volts or 120 volts or a 220 volt outlet, etc. That is referring to potential difference. All right. I'm going to skip a little bit. It is measured in volts. So the thing is, I want to point out right off the bat is the AP test does not use the term voltage too much. It uses the term potential difference. So I've had students in the past sit there and go, wait, this question's asking about potential difference. What is that? I can't answer that question when it comes to an actual test. You have to already know that potential difference and voltage are the same thing. The potential difference is really what provides the push. It's what drives those electrons through the wiring to complete a circuit, to drive them through light bulbs, through resistors, through anything that might, a motor, anything that might use that push to then create some sort of action. The other big way to think about potential difference, okay, and the one really actually important connection I want you to make is it is related to energy. Okay, it's related to energy. I want to make this clear. It's not energy, all right? It turns out the formula for potential difference, which we don't learn in this class, has electrical potential energy in it. So they are directly related. If I increase the energy, I increase the voltage or potential difference. What that means is this is the energy, or again, push, that allows the electrons to go from one part of the circuit to the other. And the main reason for that is, and why we call it a potential difference, is if you think about a battery, okay, the battery is what provides the potential difference. It creates the potential difference. Okay, that's why we have 1.5 volt batteries, 12 volt batteries, 9 volt batteries, etc. That is what's creating the potential energy. Where is that coming from? It's coming from the chemical energy inside. So again, it doesn't create it, it's converting it from one form to another form, another usable form. Okay? And what happens is it creates this because you'll probably know there's positive and negative ends to all batteries. And what that means is there's an excess of electrons on one side versus the other side of the battery. So if I connect some sort of wire and maybe a light bulb to this, we'll learn that this symbol right here means light bulb in a minute. Basically what happens is those electrons are like, oh my gosh, look at all that positive side, and they go flying out of one side and back into the other side. It gives them a potential, again, key word, to move, and the potential difference is the measurement of the difference of, again, potentials in terms of energies on either side of that battery. Another way to look at potential difference is it's basically a lot like osmosis, where you've heard of water will travel from high to low concentration. Obviously, the larger the difference in concentration, the faster the water moves. Same thing goes with potential difference. Larger the difference in charge, the greater the movement of those electrons. Okay? So, big thing, especially when we get to justifications later on. Voltage is energy, or is related very closely, directly related with energy. We have current. Current, the symbol is I. It is the flow of those electrons, and it's essentially a rate. It is the number of electrons that pass in a given time. It's how quickly those electrons are passing by. It's how many are passing by. All right. For an electrician, it's the current that they're most scared of. The current is what can cause electrocution primarily. Okay. It is measured in amperes, which obviously we abbreviate as amps, and the letter A for the symbol, or not the symbol, the unit. Okay, the abbreviation for the unit. So current is the flow. So an analogy between voltage, potential difference, and current is a river. If I think of a river, the amount of water flowing in that river is the current. The potential difference is what's driving that river, which in most cases would be gravity. The idea that that river is on higher ground and going to lower ground, there's something that's pushing that water to move along. The more water you have, the more current you have. That's where it can be more dangerous for people that don't maybe know how to swim so well. So again, that's another comparison with why current's more dangerous than voltage. Okay? You can have a very large push with a small amount of water, and that's not dangerous. Or not as dangerous. The last thing we're going to measure quite a bit is what we call resistance, which is symbol is R. And again, this is the easiest definition because it is exactly as it implies. It's the opposition to the flow of electrons. So, it's the opposition to the flow of electrons. So another definition, it's the opposition to the flow of the current. Okay? So it is measured in ohms, which is the symbol omega. But going back to my main point here, if I increase resistance, I decrease the current that travels through it. Okay? Again, assuming that essentially voltage potential difference stays the same. Now, you do need to understand there's quite a few ways to alter the resistance of the object. There's basically 4 ways. All right, all 4 of these is how to increase resistance. Okay, so the first one is make it an insulator. All right, essentially the first category would be what type of material do you have? If it's an insulator, it will have a higher resistance. Again, because insulators resist the flow, the movement of charge. So that would definitely cause more resistance. Okay, and we'll actually figure out how to calculate whether something's an insulator or conductor on the next slide. There's actually a formula that basically is a physical property of the material itself that tells you how resistant it already is. If you have thinner wires, that's going to increase resistance. For the next 3, I like to use the analogy of cars traveling down a road, except these are electrons, and electrons move very quickly down that road being the wires, and they actually move like this down the road. So here's the wire, and they're swinging around and around and around, back and forth. Now you got to imagine, again, you're talking about a billion, quadrillion, pentillion number of electrons flying down this wire at one time. What's going to happen? They're going to crash. And the more that they crash, the more resistance creates. Because if they crash, some will bounce back the opposite direction, they hit off the walls, all sorts of stuff. So there's more collisions, more accidents, that creates more resistance to a flow. So if I make thinner wires, it's just like if I go down to a thinner road or go from 2 lanes to 1 lane. If I do longer wires basically means you're giving the opportunity for the electrons to crash more because they have to go a larger distance. Higher temperatures will also increase resistance. That has to do with the fact that obviously they start even going faster and crazier. When I say crazier, not only do they go faster, which you're going, hey, wouldn't that increase the flow? They're not even moving, like you got to imagine they're not moving just straight ahead up and down, but they're moving in every possible 360 direction up and down, and this only makes them shake even more, so they're even more shaky as well. So all of these things will increase resistance, which will then decrease current. So, as I was saying, there is a physical property of the object itself called resistivity, which doesn't matter about length and area so much. There's an inherent, essentially, resistance to that particular material. So, going to the fact of like copper is often used in wires, it's because it's a good conductor. Why is it a good natural conductor? It's related to this concept of resistivity. Whoops. Okay. It has actually a very low resistivity. Okay? So, again, this is really the definition of resistivity. It depends on the type of material used, and it's just how well does it move electrons. So it leads us to a formula right here, and this formula is basically a resistance formula. So be careful here. This is not measuring resistivity. R is resistance. The resistivity factor is simply in that formula already. So you can see resistance equals resistivity factor. This is a constant. This is a constant for a particular material. But then I have to multiply it by the length, how long is the wire, divided by what's called the cross-sectional area. Even though I just have area written right here, it's called the cross-sectional area. That would be basically like you look at the wire straight on, and you stare at the wire straight on from the edge of the wire. Okay, so you're looking, like you hold the wire straight towards you and spread it away from you. Okay, not horizontal, but like, straight away from your eyes. All right. Now, you can see how this formula relates to what we just talked about with resistance. The more resistivity, the more the object's like an insulator, the more the resistance. The longer the wires, the more resistance. The thinner the wires, the more resistance. If I decrease A, this is related to thickness. Okay? So again, going back to the prior page, I forgot to do this. If you want to decrease resistance, you make it more like a conductor, you make it shorter wires, thicker wires, and you lower the temperature in general. Okay? So that formula right there supports all of those particular ideas. Be ready for area. It could either be a circle, a rectangle, or a triangle. Okay? They will say the wire is a triangular shape. Now, I've never seen triangular wires myself, but they will say it's a triangular shape. So when they give that to you, you might, they'll say, this will say the wire is a square shape. If the wire is 1 millimeter by 1 millimeter, find the resistance if you know what the length and resistivity is. You would have to find the area of this, which obviously you would just multiply the two sides. Now again, when we get to the formula, everything has to be in meters. Okay, you can see that, meters squared. So you would have to convert that before multiplying it. But that tells you about the resistance of the object itself. Okay. That then leads us to Ohm's law. Okay. Basically, we've now talked about potential difference, current, and voltage. They are all related in terms of this Ohm's law, V equals IR. Okay, V equals IR. And then, nothing too special there. Just that's going to be a very, very useful formula as we continue to do circuits. We have the charge formula. Okay, on AP formula sheet, it's written this way: I equals Q over T. Again, that can be capital Q. This just shows you that current is the rate at which charge is passing. Just remember, T is in seconds. This is not a super common formula. I did give you a little bit of practice with it. I haven't seen it too much on the test, but it's something that we need to make sure we understand could be on the test. Okay. And then that leads us to our last formula in terms of electrical power. Now, we've already talked about power. This is the exact same thing as we talked about before, where power is a change in energy over time. That is completely true still. But if I'm trying to find electrical power, I can find it by simply multiplying the current times the voltage. That tells me what the power is as well. All right, it's telling me how much energy is passing over a particular amount of time. All right, so again, that one is a very useful formula, important formula to know. There are variations, there are variations to the power formula, where power is I squared R. This is just a derivation of IV. If I do IV, but maybe the problem only gives me information about I and R, I can sit here and go, well, V equals IR, so R equals, no, not that one, sorry. I'm going to do this. Yeah, I'm doing this silly. V equals IR, so I can replace V with IR, and guess what? That equals I squared over R. I can't talk. I squared R. Okay. Similarly, if I have a problem where I'm given only V and R and it says solve for power, current would equal V over R, so this would be IV V over R times V, which equals V squared over R. This second formula is very, very useful in order to calculate or to justify the power of light bulbs. Okay, we'll bring it up a little bit later, but power is related to the brightness of the bulb itself. Okay, power is related to the brightness of the bulb. This is going to be the easiest formula to use to justify your answer. Obviously, the other formulas are possible, but all I can do and keep encouraging you is that last formula, P equals V squared over R, is extremely useful to justify and the easiest to justify. Okay, the least amount of mistakes occur when students use that power V squared over R equals power formula to justify brightness. Okay. Now, before I move on to the last little topic here, there's something that occurs in some problems that you're going to run into. You're going to run into problems where it says a light bulb has a rating, and I'll do one straight from your worksheet, of 60 watts, 120 volts. Okay? And this is what's on most packages for light bulbs. It says it has a rating of some wattage at a particular voltage. What this is referring to is this is saying if, I can't believe how important that is, if the light bulb receives 120 volts, it'll produce 60 watts of power. All right? That's a big if. All right? But why is this important? All right? Why is this important? It's actually, again, related to this bottom formula. Okay? What I can use from this formula is I can use these two numbers and figure out the resistance of the light bulb. The resistance of the light bulb will be a constant. Okay? Once you find it, based on the rating, it's constant. So I would do something like this, where I would do 60 watts equals 120 squared over R. And I think that's 240 because I think it's 240. Sorry, let me do it real fast just to make sure. 20 squared divided by 60 is 240. R would equal 240 ohms. What this rating tells you is it tells you the resistance of the light bulb will always be 240 ohms. Okay? Regardless of the voltage, regardless of the power, it will come out to 240 ohms. Again, what this was referring to is, think about how at most homes you have dimmer switches. That means you're decreasing the voltage you are sending to that light bulb, and what happens? It becomes less bright. So do you always give the bulb 120 volts? Most likely not. Most likely not. I mean, this is where some people buy light bulbs that have a much higher rating, but you never reach it. All right? But it is obviously a bit maybe safer because you'll never reach it. If you go above it, that might make it possibly explode, or obviously break, or explode, not necessarily explode, but crack. Okay? So this is just the rating is to help you calculate the resistance of the light bulb, which then you use throughout the entire problem. Okay? All right, last thing. We have what are called ohmic and non-ohmic resistors. Okay? And this again comes up in some justification sometimes, in multiple choice, and then we saw it in the free response question too. Ohmic resistors are resistors that follow Ohm's law. Okay? They have a specific resistance. What we're saying there is there's a single constant resistance, so therefore if I increase the current, the voltage should increase the same amount. If I double the current, I double the voltage. If I triple the current, I triple the voltage. If I half the current, I half the voltage. So ohmic resistors are resistors that maintain that one resistance. And those are the only ones we use in any calculation. We will not use a non-ohmic resistor in an actual calculation, but you might need to describe whether you have an ohmic or non-ohmic resistor based on what's happening. Okay? A non-ohmic resistor is one that does not follow Ohm's law. Okay? The resistance will change based on temperature. Right? And what we mean by that is, if we try to plug this in and I say I double the current, the voltage may not double. Maybe it quadruples, maybe it doubles, maybe it only halves. That's because the resistance is altering as well, so we don't have any constants. Okay? None of this stuff is constant. All right? There's no good relationship I can develop from one thing to the next. Okay? There's just a changing in resistance. But how can I tell this? Okay, there was a problem, a free response problem, where basically the question was determine how you can figure out whether you have an ohmic or non-ohmic resistor. And one way to do this is basically to graph it. There will be a very specific graph for an ohmic resistor and a very specific or a type of graph for a non-ohmic resistor. So this goes to the idea of back to linearizing our equation. All right? If I rewrite V equals IR like this, where we're trying to say R is constant, and I'm changing current and voltage, if I make this Y equals MX, where current's on the X, voltage is on the Y, that would make the slope the resistance. In other words, what type of a slope, what type of a line? It would be a straight line. Okay? So an ohmic resistor is always linear. Okay? It's always linear. It would be a linear line on a voltage current graph or a current voltage graph. Now this one's tricky. The slope of this line is not R because you've rearranged the equation. You have I on the y-axis. So that would mean you'd have to do something like this, where it's V equals IR, and you want to get I by itself. So you divide R to the other side. This would be 1 over R times V. Here's your y-axis, here's your x-axis. What would the slope be? The slope would be 1 over R on this particular section. I will say, and again, I don't go over this completely in class because I feel like some of this stuff should be known how to do this now in terms of linearization. Think about what you would get if you linearize this formula, or P equals IV, where, again, something has to be held constant. Okay? Essentially, we're not looking at non-ohmic situations here. Something has to be held constant. What if I did a graph of P versus V? The current would be I. What if I did a graph of P versus V squared? The slope would be 1 over R. Okay? So you'd have to be ready to possibly linearize any of these equations. And again, there's no squares, so it shouldn't hopefully be that difficult. For a non-ohmic resistor, we're still using the same formula essentially. This one does go V equals RI, where I'm changing the I and seeing what happens to the voltage. But what we're saying is, does the resistance stay the same? The resistance would still be the slope, but it's not staying the same. It's changing, which means it would show up as a curve. Okay? So that is what students were expected to try to write on their free response would be, I would do an experiment where I would try to change the current and see what the potential difference would do, and I would graph it. If the graph came out to a linear line, it's an ohmic resistor because the slope is resistance. If it came out to a curve, that would mean it's a non-ohmic resistor because since slope is resistance, it's constantly changing. Okay? So that is basically it. Thank you.